duration. So omega is defined as the angular distance over the duration. The angular distance would be 2 pi in what duration? The period. So the omega has this relationship with the period as well. It's 2 pi over the period t. The speed has an additional radius component. But you can see here the units of 2 pi is radians, time is seconds, so that would be the units associated with omega. Now number 5, instead of angular velocity, there is what is called the tangential velocity. We call that v sub t. Or you could simply call it v because it is the speed. So the angular velocity was how fast the theta is changing. This tangential velocity is simply how fast is it. That is why it is the speed. So the units for tangential velocity is meters per second. So the tangential velocity is defined as the change in something over a change in time. Because it's tangential velocity, you would think that it's related to the tangential position, and it is. Just like how the angular velocity omega was delta angular position over delta t, the tangential velocity is going to be tangential position over delta t. Or delta arc length over delta t. But what was the relationship for arc length that we just discussed? It is r times theta. So it would be delta r times theta. Here, let's take a look at delta r times theta, what this even means. This is equal to r times theta final minus r times theta initial. Now let me ask you guys a question. Does r change in a circular motion? The radius does not, so guess what we can do? We can factor that out so that it is r theta final minus theta initial. But what is a simpler way to write theta final minus theta initial? What is this?
Distance.
Well, but what notation? That's true, angular distance, but it is simply delta theta. So delta r theta is equal to r times delta theta. So delta r theta is r delta theta. And we just showed that derivation. But why, oh why, did we do that? Yeah, question.
I'm just a little confused about how tangential velocity is different than period, because you said that duration is period, correct? And the
No. Period is the duration for something specific.
isn't that the same as speed?
Period is a duration. Speed is meters per second. So duration has units of time. Speed is length per time.
Oh.
So the period does provide information about the speed. You are correct. But the period only gives the duration to complete one revolution. The speed actually takes the distance traveled in that revolution and normalizes it by the period. Okay, so why, oh why did we do all of this? because we can plug it into here. V of t, we are going to replace the delta r theta with r delta theta. So this is going to be equal to r delta theta over delta t. But what is delta theta over delta t? What did we just discuss that it was? It is omega. So the tangential velocity is simply r omega. That is why we did all of this to be able to extract this nice relationship. As long as you know omega, just multiply it by the radius and you'll get the tangential velocity. Of course, alternately, we would know that omega is also equal to the tangential velocity over r. That's it. Now, I understand this derivation, you may not have done it before. So as a method of double checking, you can always check your units to see if they actually end up working out. What is the units for omega? What are the units for omega?
RPM.
Huh?
RPM.
Okay, yeah, RPM, but let's do the more SI unit one, which is radians per second, right? Radians per second. Let's make sure that the right-hand side actually works out. What is the units for tangential velocity? It is meters per second. Divided by, what is the units for radius? It is meters. You're going to see that the units for meters cancel and you're left with 1 over second. Uh-oh. Are those two equal? Alright, so apparently we did something wrong. Except we didn't. This is actually right. Radians is actually not a unit in the fundamental sense. Radians is not a unit. It is actually a unitless or kind of a dimensionless quantity. But this radians helps convey the idea that something about angles is occurring. Something about angles. Like angles is not a fundamental unit of measurement or anything like that. Like mass, it actually means something. Distance, it actually means something. Angle, what is an angle? So even though these units might not look to agree, they actually do. So essentially radians is, you can drop it and it's technically okay. But let's make sure that we are keeping in mind the difference between these two. So the angular velocity omega is just referring to how fast the angle changes. Whereas the tangential velocity is, okay, now that you know how much the angle changes, what is the actual distance associated with the angle change? Let's do a quick example. Let's say we have a rotating disc. So there's our circle. Let's say 2 marks are made. A and B, and we make it here, A, and here is B. Let's say we rotate the disc half revolution. So when you do that, the A is going to make this semicircle, B, we'll make that semicircle. Do you guys follow? Yeah.
Sorry, I'm just trying to understand. So I thought that we don't rotate it. We're not measuring the rotation.
So we're not measuring the rotation of the disk, we're measuring the rotation of the point. What shape is it making?
Okay.
It's a circle, right?
Yeah.
And so in like spots on an object that's rotating will make a circle. But we're not trying to analyze the full disk here, we're just trying to analyze this circle as well as this circle. That's what we're trying to do.
Got it. Thank you.
Now I'm gonna ask two questions regarding this scenario. The first one, which is true about omega? Is it A, omega A is greater than omega B? Or is it B, omega is equal to omega B? Or is it C, omega A is less than omega B? Or D, not enough info? Likewise, we're going to ask the same question about the tangential velocity. So question 2, which is true about VT? Is it A, VT of A is greater than VTB? B, they are equal? C, is A less than B? Or is it D, not enough info? Alright, let's see by show of hands. So we have this scenario where we half rotate this disk with 2 marks on it. Which is true about the angular velocity omega? Who says omega of A is greater than omega of B? Raise your hand. Alright, who says they're equal? Raise your hand. Who says A is less than B? Raise your hand. Alright, who says D, not enough info? Raise your hand. It is B. It is B because both of these are traversing theta of pi, or 180 degrees. So both of them have theta is equal to 180 degrees. So omega is the same because omega is equal to delta theta over delta t, and delta theta is equal to 180 degrees for both, and delta t is the same for both. So if the numerator and the denominator are the same, then the omega is the same. Here's a mosquito. So the omegas are the same. Well, what about the tangential velocity? Who would say the tangential velocity of A is greater than that of B? Raise your hand. Who says they're equal? Raise your hand. Who says A is less than B? Raise your hand. Who says D, not enough info? Raise your hand. It would be C. Now, why is that? Remember, Vt is delta S over delta T. We already described or defined that delta T is the same. Delta S is actually the length of the line. Which line is longer? This line or this line? The line for B is much, much longer. Yeah, delta B, the line for delta B is much, much longer in the same time frame. Or we can also recognize, remember the Vt was r times omega, which is equal to r omega. In the first problem, omegas were the same. So the only difference then is which one has the larger radius. The one with the larger radius for the circle would be B. So here RB is greater than RA, and omega A is equal to omega B. That's why it is C. The tangential velocity of B is greater than that of A. Now on to parameter number 6. The last 4 are all accelerations. There's 4 accelerations that we will be considering. The first is what is called centripetal, or the radial acceleration. Now there was a few questions about 17C in the problem set. I did make a mistake. That should not have been assigned, because we're going to cover that now. So when there's an object moving in a circle, let's say uniform circular motion, so the speed is the same, we can draw their motion diagrams by drawing the following. We draw that, then draw that, and draw that, 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 and then that. So we kind of discretized his circular motion, and we chopped it up into a few different pieces. These are the velocity vectors v. But what we're trying to do is draw the acceleration vector onto here. Now let's remember how to draw the acceleration vectors. So if we have velocity 1 and this is velocity 2, how to get velocity 2 from velocity 1? You would need to add the acceleration vector A. So then this vector plus that vector gives you this vector. So here you would put the first vector here, then the acceleration vector you would plop on top of it. That's how you would get the new velocity vector. Let's do that same idea over here. How do you go from this to that? You would have to add a vector pointing in this direction. So this vector plus, I think that was a little bit too long. I think it should have been something like that. So this vector plus that vector will give you now this vector. Well, what about between here and here? How do you go from here to here? You would have to add this vector. And likewise, for every other one, it'll look like this, like that, like that, like that, like that, and like that. What direction are all of the acceleration vectors pointing? What direction?
Inward.
Huh?
Inward.
Yeah, towards the center of the circle. So acceleration is toward the center of your circular motion. Central. So note even at constant speed, object accelerates. We have to remember acceleration is not just changing speed. What was the definition of acceleration? Velocity changing. Velocity has two components: the magnitude, which is called the speed, as well as the direction. In this case, the speed was constant, but the direction was changing. You guys see that? The direction has to be changing for it to move in a circle. So there definitely is an acceleration associated with circular motion. Even if the speed does not change, the direction does. The direction of the velocity does. And so the centripetal acceleration, we call it ACENT. Or sometimes, because it's the radial acceleration, we also say A sub r. Both of those would be okay. This is defined as the acceleration due to a circular trajectory. If it's moving in a circle, it will have this acceleration value just by moving it in a circle. An object wants to just go straight, but you're preventing it from going straight, and you're trying to close this on itself, and that is the centripetal acceleration is the acceleration associated with trying to close it onto itself. So that is that acceleration value. And just like how things like the tangential velocity was very nicely related to things like the omega, there's a very nice relationship that actually gives us the acceleration value for us. And this centripetal acceleration is equal to v squared over r, or vt squared over r. But remember, Vt was equal to omega r. So meaning, it would be omega r squared over r. Sorry, omega r quantity squared over r. The exponents distribute. Simply, you would get omega squared r squared over r, and one of those r changes. So you would also get omega squared r would be equivalent. So we can tackle that onto here as well. So as long as you know what speed you're traveling at, or the angular velocity you're traveling at, then you also know the acceleration associated with it. So here this is saying the faster it goes, the more you have to accelerate to make a circle. And I'm sure you guys have all felt this when you're driving in a car and somebody makes a sharp turn and you hit your glass or you hit your face on the window and it's going to hurt. Right, that's the whole acceleration thing happening. Yeah.
Why did you divide by r up there?
Here? Oh no, yeah, it's omega squared r. Sorry. Yeah, that's a thing. Omega squared r. Yeah, it is actually good. And so if you do the units for this, it'll be meters per second squared, just like a normal acceleration value would be. Yeah.
What's the overall value for centripetal A? Is it just a cent? Or what?
Yeah, the notation for it, yeah,
Yeah.
ascent or a sub r. ACENT.
Sorry, Mr. Camp.
Yeah.
Why are you dividing VT squared by T or by R?
Okay, this requires a calculus for the derivation, so we can't, like, we're not gonna get there. Yeah. Although, could I shorten it up? It's gonna take a little bit too long. I can show you after though.
Alright,
Yeah.
alright, thank you.
So note, this acceleration is the centripetal acceleration. The centripetal acceleration vector always points towards the center of the circle. And you do have to specify this because we have 3 different accelerations to go. And we don't want to be confusing the two, confusing all of them. So it's just important to note, ascent only deals with speed. Or sorry, only deals with direction, sorry, not speed. Only deals with direction, not the speed. Well, because of that, there must be clearly a acceleration type that actually deals with the increasing speed, and you are right, and that would be number 7. That is called tangential acceleration. Tangential acceleration, a sub t. And this is the acceleration associated with changing speed. If it's changing speed, you know that you have a tangential acceleration. Because it's associated with changing speed, this is going to be delta Vt over delta t. So this is the tangential acceleration, but like position and velocity, there is that angular component with it. So number 8 is what is called angular acceleration. That, we give it the Greek letter alpha. And alpha is defined just like how, let's get to the other angular. Angular velocity was delta angular position, delta t. Angular acceleration is delta angular velocity, or delta omega, over delta t. And has units of radians per second squared. But with this, let's quickly come back to tangential acceleration for a moment. Tangential velocity, we discussed, was equal to r omega. The tangential velocity was delta r omega, delta t. But like before, the radius, does it change? In a circle, it does not, so that can actually pop out of our delta. So this would be r delta omega delta t. But what is delta omega delta t? We defined it down here to be what is called alpha. So the tangential acceleration is r alpha. And so you can see that the different acceleration values are related. One is simply the other times the radius. We're not done. We have one more to go. And that would be number 9, the total acceleration. Where the A total, of course it's a vector, it's just sum of its components. A tangential plus a centripetal, or that's the radial component. And so the magnitude, that is simply the, using the Pythagorean theorem, a centripetal squared plus a tangential squared. There you go. Yep, these are a lot of things to now not just remember, because you're not trying to memorize it, but you actually want to know it to the point where you can actually use it. If it's just rote memorization, then you have no intentions of using it. And of course, we need, in physics class, a deeper understanding of that. Now, luckily, most of these we're not going to use. You actually just, you needed some exposure to all of this so that you can see actually the complexity behind these different types of motions. Okay. So the most important ones I will highlight likely next week because we are running out of time. Well, let me summarize all of this for you. So let's do a quick summary. First is the position. We went from x and y to r, theta, and s. R, theta, and s. Here, well, actually, let's put it this way. Radius, theta, and s. What was s equal to? R theta, which is the radius times the theta. Well, what about the velocity? We went from just Vx and Vy to omega and Vt. Omega was delta theta, delta t. But Vt was r omega. Last week, acceleration, we had a centripetal. We also had alpha, which was delta omega, delta t. And the tangential acceleration was r alpha. And of course, we had that the total acceleration as well. Well, look right here. Everything on the left is the angular. Everything on the right is the tangential. Do you guys recognize a pattern? The tangential is simply the angular times the radius. That is it. Tangential is simply the angular times the radius. So you can memorize all these 9 equations. You are more than happy to do that. Or you just take the shortcut way and remember tangential is r times the angle. Of course, we need to know what they mean. Omega is simply how much the angle is changing per time. How fast is the angle actually changing? Whereas the speed is, okay, I don't care about the angle, I actually care about how large is that circle, how large of a distance was actually being traveled in the unit of meters. Alpha is referring to how fast the angles, or how fast the omega is changing. You can begin here, the circle. Alpha, you can begin the circle here. You can begin kind of slow and then get faster and faster and faster. That would be alpha increasing. In this case, we don't just care about how fast the angle is changing, but how fast is the actual distance that the amount of ink or the length of ink, how fast that is changing. So one is just the angle, the other one actually has to do with the physical distance itself. I think Shina, yeah, I think you asked a question about something along these lines a little bit while ago. Although now I kind of forget the context of the question, so I forget.
It wasn't the swing.
Oh, with the swing. No, that was today. But I think you asked a question like a week ago. Something along these lines. Oh, well, if you don't remember it, I don't remember it either. So. Okay. Now, with this in mind, and maybe you remember this whole delta t thing from before. Do you guys recognize this from somewhere? If you don't, that's okay. For circular motion, we also have kinematic equations. And this, in terms of solving problems, these are of greater value. Right? This is the heart, and hopefully doing the projectile motion problem set really, got you guys to memorize the kinematic equations. So for constant alpha, we'll do this. For constant A in the s direction, we have Vs as a function of t is equal to V naught s plus AST. Also, S of t is going to be equal to S naught plus V naught st plus 1/2 AST squared. All right, does this ring a bell? Hopefully it does. All right. Hopefully it rings a bell. We have pretty much the identical thing for all of the angulars. So constant alpha, you have omega as a function of time is going to be equal to omega naught plus alpha t. Likewise, we have theta as a function of time is going to be equal to theta naught plus omega naught t plus 1/2 alpha t squared. And look how close these equations look to each other. You're just swapping out one parameter with the other. And some of you guys are going to be thinking, all right, these are two more equations to memorize. Okay, well, I'm not going to believe you because they literally have the same form. You're just swapping out the parameters. And even with these two additional ones, I would still say you really only have like 4 equations to memorize so far. This is one, that is another, and maybe there's a few other ones that you want to memorize. Likely, if you looked at some of the problems in the example, you may have seen these other equations as well. You would have VF, we'll do this. VF squared is equal to V naught, in the S, squared plus 2AS delta S. Did your textbook use this equation ever? Anybody ring a bell? You are free to use this equation too if you want. I don't recommend it. I never use it because it provides no new information from here. This is just rote memorization where you don't really know what's going on and you just blindly plug in and chug. So you're allowed to use it, but I don't ever use it myself. Now let's put all that into an example. The example, and I in no way condone gambling, but roulette is the prototypical circular motion type of a problem. No extra credits will be given if you guys do this. Okay, no extra credit. Let's say a steel ball rolls counterclockwise inside a 50-centimeter roulette table. You're also given the ball complete two revolutions in 1.50 seconds. And you're asked two different questions. What is the angular velocity of the ball? Question 2, what is the angular position at 2.5 seconds? So these are the questions. So what is the angular velocity of the ball? What are we even looking for here? What parameter? Angular velocity? What symbol do we give it? Omega. Oh, thank you for not saying W. Sorry. Omega. Omega. We want to know omega. Let's just remind ourselves what omega is defined as. What is it? Yeah, delta theta over delta t. So delta theta and the delta t associated with that delta theta. Are we given that kind of a parameter? And the answer is yes, we are. 2 revolutions in a certain duration. 2 revolutions means 2 times what is how many angle? What is the angle that's traversed in 1 revolution?
2 pi.
2 pi, right. I wanted radians, not degrees, right, 2 pi. All right, 360, technically you would have been okay too. In 1.50 seconds. And so just by looking at the definition, you realize that you have all the information, and then you are done. So that's radians per second, and so if you actually do that, you would get 2.667 pi radians per second. That would be the omega. So you can't just blindly go into your kinematic equation and hope all magic works out, because sometimes it will not. Sometimes you have to actually just go back to the definition and you'll find out, oh, I actually have everything I need. Now, secondly, we want to know what is the angular position? So where, or which theta value will the ball be at in 2.5 seconds? So for that, theta t is equal to theta naught plus omega naught t plus 1/2 alpha t squared. The reason why we went here is because what were we asked for? We want to know the theta at 2.5 seconds is equal to question mark. And because this was what we were asked for, well, hopefully at this point it's intuitive that you would just go straight to that equation. And then we assess. Do you guys know everything? One of the things that we're going to assume assume theta naught is equal to 0. So wherever the roulette dealer, whichever point he actually releases the steel ball, that we're going to be established as our reference angle theta. So we actually do know this, and it is 0, so we can cancel it out. Do we know omega naught? And yes, we do. We just solved for it in part A. Although we called it omega. Do we know time? What is it? Yeah, 2.5 seconds. The time was given to us in this problem. Do we know alpha? No, but we're not given any information about it, so let's just make our lives easier and take advantage of the fact that it was ambiguous, so you can assume it to be 0. There was no information provided for us. And so we know everything. So theta t is simply omega naught times t, which omega naught is 2.667 pi radians divided by per time times the time is 2.5 seconds. The units for seconds will cancel, and then you're going to see that this is going to be equal to 6.67 pi radians. So where is it? It is at 6.67 pi radians. Yeah.
Why do you not multiply the number by the pi?
How many digits are in pi? Infinite. It's not just 3. It's 3.1415 and yada yada yada. You want to write all of that, or would you just merely do this? And pi is actually significant. We're actually going to get to a more precise reason why, but in just a moment. Yeah.
So if on the quiz, if we were to put pi in like our calculator, and the answer didn't come out as 6.67 pi, but rather a different number, would you accept that or no?
Yeah, I would accept it. Well, I would think badly of you because you did more work. No, I'm just kidding. Are we finished? Did we get what we want? Who thinks we finished? Raise your hand. Who thinks we did it? Raise your hand. Okay, but if we did it, why not? Why didn't we? Or how'd you come to that conclusion?
You're a tricky guy there.
I'm not a tricky guy. We did not finish, even though this is actually what we were looking for. The reason why we're not finished is there is a convention that we have to follow. In a circle, how many radians are there? In a circle, how many radians are there? 2 pi. Is this within a circle? And it is not. So in a circle, essentially what we did was we made one revolution, then another one, and then we went a little bit further. We are the one tasked with doing the hard work, so instead of telling the person how many revolutions when they're just asked for where is it, we just have to give a number that is actually between 0 and 2 pi. The convention position should be between 0 and 2 pi. So because we know each revolution is 2 pi, we just take this number, and so theta 2.5 seconds then is going to be equal to 6.67 pi minus some n, which we don't know what that is yet, times 2 pi. And this n value is going to be the number of rotations. And you just keep changing this number until we get a number that is between 0 and 2 pi. In this case, what should n be? Yeah, if n is equal to 3, you're going to see that you get 6.67 pi minus 6 pi, which is going to be 0.67 pi. And this would be a sufficient answer. So now, Sierra, now to answer your question. Let's say we have this, that's our circle, that's our theta naught. The reason why we want to keep pi as in this form is in one revolution there's how many pi's? 2, meaning in half a revolution, how many is there? 1. So here, this is pi. And if we're at 0.67, where are we? We are slightly past the halfway, and it will be right here. This is very easy to see because we have it in terms of pi. But if you actually multiplied out the pi, then it would be like 1.8. It's like, what is 1.8? It's a little bit harder to tell. But with this pi in there, it's 2/3 of half of this. Right, very easy to see. That's why we want to keep the pi in there, yeah.
What does n mean again?
N is the number of revolutions. But you just keep changing it until you get this condition satisfied. So n would be number of revs. Well, this is all I got to in the earlier section, so we will end it here. Now, just a reminder, projectile motion is much more central. It will be on the quiz tomorrow as well as on the quiz next week as well. So a single studying now will be studying for essentially 2 different quizzes, plus one of the primary subjects in the exam. So all of your studying efforts this time around will pay great dividends.